Okay, so this lecture is about regression or linear regression or regression with one variable. This is also called univariate regression. If you remember in first class when we were looking at the taxonomy of different machine learning setups and algorithms, we talked about supervised machine learning. And in supervised machine learning, there are two different kinds of algorithm. The first one is classification algorithm, and the second one is regression. So in classification, we have a discrete set of classes, and we try to predict those discrete set of classes. But regression output is real value. And as you progress in this lecture, you will understand what I mean by real valued output. So these are reference books for this module. There's chapter 1 and 3 in Bishop's book. You will find text on regression and linear regression, and in Tom Mitchell's book, you can find text on regression in chapter 8. So you can refer these two books for this module. So this is problem setting. Here we are saying set of real valued instances X. This is our data set as usual, like in our supervised machine learning algorithm or classification task. So this is our data set X. Unknown target function F. We try to find F that maps X to Y. Y is our output or target variable. And we try to find hypothesis of function that maps input to output. This is same as classification. There is no difference over here. Training examples again are given as a vector xi, yi. Xi could have d dimensions and yi is the output corresponding to input xi. But what kind of learning is this? This is regression. The output of regression consists of one or more continuous variables. Instead of predefined concepts or classes, now we have continuous variable that we want to predict, and this is called regression. So let's say if this is classification, this yi, usually we see binary classes. So they were like +1 or -1. So we try to predict whether the input feature vector belongs to class +1 or -1, or it could be like many other classes, 10 classes, 20 classes, 30 classes, doesn't matter, but they are like discrete. But in regression, we try to find map input to discrete or continuous values. So let's say if input is 1, 2, 3 and output is 2.4, and if input is 2, 4, 5, output is 3.1, something like that. So there is no predefined notion of classes in regression. But again, we try to find H hypothesis that best approximates target function F. So let's look at the intuition or regression. So you will understand better what I mean by regression. Regression is mapping of continuous inputs to continuous outputs. So continuous inputs, this is our feature vector, xi, and continuous output is denoted by yi, simply, right? So let's say this is the data set given to us, and this is data set related to salary of a person based on his or her experience. So let's say if experience is around 1 year, um, the person is getting salary something in the range of 30,000 Ks. In the same manner, if experience is around 2 years, person is getting salary in the range of 60 Ks, right? And let's say if someone asks you, if I have experience of 2.5 years, what would be my expected salary? So what you can do, you can just draw a line that approximates this kind of data, and you just plot 2.5 over here, and if 2.5 comes over here, you can say, okay, salary is around 60, something again in the range of 60. So this is like approximating the data given data set to us, and based on that we can predict real valued outputs. So the concept I am trying to give you is what is meant by real valued outputs. If this is a classification rule, we would have classes like if experience is 1 year, person belongs to class 1. If experience is 2 year, person belongs to class 2. But we could have like 1.1, 1.2, 1.3, and output could be also in real value. So this is the task of regression. Why regression is called regression in machine learning? This is very interesting story, and you can read in this paper. I have given you a link, but I will briefly discuss why regression is called regression. Regression, as per dictionary, means to return to previous and less advanced or worse state. So regression means to go back to roots, to go back to its roots of something, to go back to previous value. But why regression is called regression in machine learning? That is very interesting question. So this is the paper, and I suggest you to read this paper because first regression uh, for the sake of machine learning or statistics is used in this paper. This is a paper from 1886 and it is available in from this hyperlink. I will briefly discuss. So this is the illustration from the same paper. So according to psychoanalyst Sigmund Freud, regression is defense mechanism. Regression is defense mechanism, right? And this is a paper from psychoanalyst. So this Galton was psychoanalyst, and regression is defense mechanism leading to temporary or long-term reversion of the ego to an earlier stage of development rather than handling unacceptable impulses in a more adaptive way. So this is the text from his paper, but I will explain what I mean, what this paragraph means. So in machine learning, the usage of word regression is linked to article by Galton. In this article, Galton showed that average height of population regresses towards the mean. What he did, Galton, he did a survey of heights of individuals and their children. And what he found was very interesting. So this is the plot of his survey. So let's say if parent, so on x-axis is the height, and this is in descending order or ascending order if you think like that. This is on the x-axis, right? So he plotted height of a person and his children on this scale, and he saw that if a parent or father is short heighted, because this is the mean around 68.2 inches, let's say. So if this is the height, so that it means parent is less than mean. But if you calculate or measure height of his children, you will find the height is bit more or children are more taller than their parents. So this is the average height of a children for a parent whose height is around 64, let's say, inches, and children height is around 66. But on the other side, if parents are very tall, let's say they are 72 inches tall, their children height tends to be less than their parents. So it means that children are trying to, the height of children are going towards their mean. You can say that you can see from this graph that children height is regressing towards the mean or the previous stage. So this is the mean height of the population. So from here this regression comes into statistics or regresses towards the mean. This was the sentence from his paper, and from there this regression terms came into statistics and then in machine learning. So this is very interesting paper to understand what is meant by regression historically, and I suggest you to read this paper, and you can download this paper from this link. Any question up till now?
No, sir.
All right. Okay. So let's say again, this is the data set. This is the toy example I'm giving you. This is the data set of experience versus salary. So if a person's experience is 1 year, the salary is 30K. If experience is 1.3 years, salary is 33K, so on and so forth. And we are given set of real valued inputs. So these are our inputs, like in classification problem, and we are trying to find a function that maps input to outputs, and this is the output. So our output is also real valued. There is no predefined notion of classes or labels or target variable, but this is real value. So if you go, let's say if you go deep into this data set, you will find there are thousands of different salaries given. So there are no predefined notion of classes, but it's real valued. So if you see from your high school mathematics or your first year calculus class, this is like a straight line. It's like fitting a straight line to the data, and that is the line of regression. This is linear regression line. So it's a linear function which is given by mx plus c. In books you will find theta notation as well. I am using mx plus c because this is more intuitive. But in books you can find notation something like theta 0, theta 1, and so on and so forth. And this hypothesis, here I've written y, but in some books this is written like h of theta. So if you're given like this notation, don't confuse with the notation. This means these are the parameters of regression line. So here I'm denoting this theta by m and c, but you could have any notation, theta 0, theta 1, theta 2, and so on and so forth. So don't get confused with the notations. So this is an example of linear regression with one variable, as I told you before, and this is also called univariate linear regression. This is just like fancy name of saying this is one variable. It could have multivariate. We could have multivariate linear regression as well. So now I'm going to ask you, if I give you this kind of data and you want to fit a line, how you can fit a line? Either using knowledge of calculus or random searching a line or a brute force. What would be your answer? Any
Sir,
thoughts?
brute force. Sir, brute force क्या होता है exactly?
Brute force means you try each and every option. Brute force, like you don't know intuition, you don't have any mathematical background, you just try each and everything, and you suppose you'll find the best out of, let's say you try a million different options, and out of that million, only one is the right answer. So that is kind of brute force algorithm.
सर तो कैलकुलस मेरे ख्याल है ज्यादा सूटेबल रहेगा.
Exactly. Exactly. We'll use our knowledge of calculus to fit a line or to find a regression line. Right. So best line will be the one that minimizes the error between line and the data point. Because let's say this is the data set and there could be different lines. This is also one of the line and probably this is one of the line as well. But we try to find best line, and best line definition is best line will be the one that minimizes error between line and data point. And we'll find this line using least square error, and I will explain what is mean by least square error. But the idea is we need to find best fit line, right? Best fit line means the line which minimizes the error or which is as close as possible to all the data points in simple terms. So let's say I want to give you kind of intuition how this parameter M and C would reflect on the line. So here I have three examples, one example, two, three, and I will show you by changing the different parameters what would be the effect of these parameters on the line. And probably from your high school mathematics, this would be like a refresher for you to understand if I change C and if I change M, what would be effect of these parameters on the line. So let's say if C is 1.5 and M is 0. So if this is the equation mx plus c for our hypothesis, m corresponds to slope and c corresponds to y-intercept, right? We know that from our high school. And here I'm saying c is 1.5, so it means line y-intercept is over here, 1.5 over here. And slope m equal to 0 means there is no slope. This is a straight line. So if m is 0, this would be like this. If m is 0 and c equal to 1.5, this would be the line. Right? Again, right. This is the line. You get an idea, Osama and Ariba?
जी सर.
Right. Can you give me answer what would be line corresponding to these two parameters? What would be the effect of C? If C equal to 0, what it means?
सर तो लाइन जो है वो रीजन से पास करेगी.
Exactly. If C equal to 0, it means line is passing through a region. And M equal to 0.5 means if it is 1, it will be like, just like, what should I say? Slope 5 mean is less than 1, so this is something like this, right? It is going upward direction with the slope 0.5, simple. And if C equal to 1, it means y-intercept is over here, m equal to 0.5. In similar terms, it would something like that. Simple. So you get an idea by changing C and m, what is happening to the line? And these hypotheses or these lines could be denoted by this mathematical notation. F of x equal to 1.5 means this is a straight line which passes through at y-intercept is 1.5. This could be written at 0.5x because this is passing through a region, there is no C, and these two parameters could be mathematically written like this, 0.5x plus 1. So if in terms of theta, you can write it like that, h of theta is equal to 0.5x plus 1. So this is theta 0 and this is theta 1. So this is just notations. You can use different notations. So now we are trying to find best line or best constant line. I am giving you two different scenarios just to give you an intuition how you can find best fit line. So let's say we are trying to find line which is given by this hypothesis f of x equal to c. F of x equal to c means there is no m. M is equal to 0. So there is no slope. So it's a constant line without any slope m, and that line gives same output for any output. So this is like, if you remember, this is something like this. If I give you this kind of problem to solve on a given data, and I want you to see how you can do it. So this line is something like this. The data is given over here, and I'm asking you to find best fit line without any slope. So probably this would be best fit line. So how to do it, how to find what would be the line given the data set. If you remember in second or third class, we looked at different loss functions. Here we will use loss function to find best fit line because best fit line is the line which minimizes the error. And this loss function are here to calculate errors. We saw different kinds of error and I want you to answer me which error is the best one used in this situation. We saw 0-1 loss or 0-1 error, which is just like looking at output of a classifier or hypothesis and output given in the data set and matching it. So if this is, they do not match, we count as 1. So this is exactly opposite of finding an accuracy. So this is 0-1 loss. I'm just giving you a reminder. You have already seen this one. The second error function we saw was sum of squared loss or sum of squared error, and this is given by this metric, right? Very intuitive, everyone knows it. And absolute loss is almost same as sum of squared loss. Here we are squaring this term, and here this is absolute. And h of xi is the output given by our regression line, and yi is real or the target output. So this is predicted output minus real output or target output, and you scale them up, and 1 over n is to find the average. So there are n samples in our data set, You divide by n to find average sum of squared loss or sum of squared error. Over here again, this is 1 over n just to find an average, and this is again predicted output minus real output or target output, and you just get the mod of it. So according to you guys, which one would be the best loss function for regression settings?
सर एब्सोल्यूट लॉस होगा ना.
Absolute could be used. So we can just say that this is not possible in regression because as we were discussing initially, if output is 3.1, let's say we predicted output and target is 3.05, according to this would be this would not be correct and would be counted in error, but for regression sense this is very close value and this could be taken as a correct output. So this cannot be used for regression settings. This is typically used for classification loss. These two losses can be used for regression, but usually we use sum of squared error because this error or this error function is convex, and convex means that there is one local there is one global minima, and I will explain what I mean by global minima. So usually we don't use this one for a regression. We use this formula loss function because this function gives a convex function, and convex functions have very nice mathematical properties that are exploited in machine learning. So sum of squared
सर
loss will be,
एक
yeah, yeah,
जैसा हमने पहले डिस्कस किया था कि जैसे जो सम ऑफ स्क्वायर्ड लॉस है इसमें अगर डिफरेंस जो है वो इंक्रीज एरर जो है वो इंक्रीज होता जाएगा क्योंकि वो स्क्वायर कर रहा है फंक्शन, तो वो वाला
right.
प्रॉब्लम नहीं आएगा.
Yeah, this is one of the issue. But as I told you, this function, this mathematical function has a very nice property that this is convex. And later on, we have to find derivatives to find maxima or minima of a function. So this loss function is preferred. Because of mathematical convenience, this is used more. But that has to be dealt, you are right. But for other reasons, we use sum of square loss, right?
राइट सर. राइट सर.
Okay. So, so this is the data set we are given. This is the data set this is given to us, and we are trying to find best fit line of constant line, as I give you before, without any slope, and we are using this error function. This is sum of squared error function, where yi, as told you before, is actual or target output, and C is predicted output because prediction is C, right? This is our hypothesis, and we are saying that let's say h of theta over here is equal to C, and we are saying that this is the output. So this is the output. Sometimes it's written as y hat previously, but now we know that this is C. So yi minus C and squared. So this is sum squared error, and we are trying to minimize this function to find best fit line for this data set, this line, right? This is very intuitive to know, okay, what is happening. Now the thing is, we have given this function, and our task is to minimize this loss function to find best fit line. And now my question is how you can find C that is minima of this function, because this is the loss function. We want to minimize it, so we want to find C that gives minimum value for this function. And you have to use your calculus knowledge to answer me how we can find minima of a function. Yes, please. Any one of you. So if you use your calculus knowledge, Probably you have heard this algorithm, Fermat's theorem, not algorithm theorem, which says that if there is a function which has a local extrema, extrema means minima or maxima, at point A and f is differentiable at A, then this would give you 0. This thing would give you 0. So this just says that to differentiate a function and equate it equal to 0 to find C that minimizes this function. Any question?
No, sir.
Okay, so now if you understand this theorem and you apply this theorem into equation 5, we can find C. So you have to take derivative of this loss function with respect to C because we were trying to find C. Y is already a constant value, we know that. We're trying to find C, so we'll differentiate C. And when we differentiate, we'll know how much error wiggles as a function changes in C. So we'll differentiate this function, equate it equal to 0 and find C. Can you do it mathematically on your copies right now? Osama, I can't, your mic is on, but I can't hear you.
हाँ जी सर, एक मिनट मैं इसको करके देखता हूँ.
Okay, I'm giving you 1 minute and then I will solve with you. Just try to solve it by yourself to understand how you can differentiate this function. Ariba and Osama both, and I'll explain you then later on. So take 1 minute. Okay, I can solve it for you guys and you can just see, right? So this is the function, error function given to us. And we are differentiating it with respect to C, right? So we'll differentiate, we know that this 2 would come down over here, 2 summation yi minus C, and 2 would be minus 2 minus 1, this would remain over here, and then they differentiate this inner term. So this is yi, y as constant, we don't need to differentiate, and minus C because we are differentiating it with C, so it would be minus 1. Minus C differentiated with respect to C would give minus 1, right? And now we can just make this equal to 0. That is Fermat theorem. And we can just solve it for C. Right? See, so this would be 2 summation yi minus 2 because this minus 1 would come over here. So minus 2 equals this and then 2 summation C plus, because this is minus and this is minus, that will equal to plus, and we will equate equal to 0. So this is minus, this term would go on the right side, so this would become 2 summation C equal to 2 summation yi. The 2 2 would cancel, and this summation goes I equal to 1 to n. So if this, and this is constant c, we already know that. So if constant multiply added 10 times would give n into c, we can write this would give same answer, equal to summation yi, and c would be equal to 1 over n summation yi. Now this is very interesting result. And can anyone tell me why this is interesting, or what is this term? Any one of you?
सर तो जो सी की वैल्यू होगी वो एवरेज पहले से ही हो रही है, इस वजह से
Average.
एरर।
Actually, this is the answer. This is the answer. This is the average value. C that minimizes this error is the average value of the data set, because this is outputs. So you add all the output divided by n, and this is also I goes from 1 to n. So what this equation is saying, to add all the outputs divide by n. So you add all the output divide by number of samples. This is the average, simple average as we know it. So if we are trying to find a constant line with no slope, this means this is the average value of the data set is the output, which makes a lot of sense as well, right? So again, this I have solved by hand in my previous slide, but this is given over here as well. So C is yi divided by n. So sum of all the outputs divided by n, which means that you output average value, and you just, so let's say if this was your data set given like this, these are the outputs, or we were looking at salary and this was experience. So you just count all the salaries, divide by n. So you'll find something which is mean value, let's say over here, and you draw a line over here. So this is regression line with no slope, right? It makes a lot of sense. It's very intuitive. Do you understand this concept? Any question up till now?
नो सर।
Right. So in the same way, I can ask you try to find a line with which passes through a region. So mx plus c is our hypothesis, and if c equal to 0, then our regression line would become mx simply. So mx means there is a line with c equal to 0. This could be this line or this line, or could be something like this line. And in the same way, you can find a line which best approximates your data set if it passes through a region, if you just constrain yourself, and we can solve it in a similar way. In similar way, we can do it like instead of minus c in previously, now we write minus xi, and now we are trying to find m that minimizes error, because m is the parameter, xi is just the input, so we differentiate with respect to m, and we can solve in the same way, and we'll find a line that passes through a region which best approximates our data set. So this could be done in both ways. So this is the intuition, like if this is the data set, this is the same data set which I showed you over here. Let's, I guess it was, yeah, here. So this was the toy data set which I showed you earlier with experience and salaries starting from 30K and going upwards, experience starting from 1 year and going upwards. And if I plot this data set, it is something like this one, experience starting from 1 going up till 7, salary starting from 30Ks and going up till 90Ks for experience of 7 years, and using the same mathematical intuition. We can find a line which is constant line without any slope, and we can find a line which passes through region. And if you do calculation like I showed you before, this would be line which is constant line, and this is average value of our data set y equal to 6 0 2 3 1, and you can just draw it. So this is very bad approximation of the data, but this is one way of looking at regression. But if you constrain yourself to y equal to mx, and you say c equal to 0, so line passes through origin over here, you can find line something like this, like this. So you can just solve mathematically, you find the equation, you put the values, and you'll find the line which best approximates this data set, right? This is quite intuitive and gives efficient answer for regression. So this is intuition of regression. We'll see mathematically how we can optimize different parameters and minimize this loss function to find different parameters, but this is the intuition. So any question up till now? Any query?